All right. In his best-selling 2011 book, Homosapiens, Yuval Noah Harari discusses a history of humankind. And one of the core ideas in this book is the importance of words and the importance of stories. Words and stories are what unlocked our potential as humans, whether that be your religion, your nationality, the company you work for, or your ability to tell your fellow cavemen and cavewomen that there's a lion down by the watering hole, don't go to the watering hole. Our ability to get people behind an idea is fundamental to our success. Now, I know what you're all thinking. James has been on the Guinness already. This is serverless days, not a talk about human history. But this is really important because there's a link here, and the link is with event-driven architecture. Because event-driven systems let you tell the story of your business through its technical implementation. The language of your business is what's driving its functionality. And that's what you're going to learn about in this final talk today. We're going to take a bit of a look backwards at some of the history of event-driven systems and how we ended up where we are today, some of the patterns that exist in modern development, and then look further forward at what the future of development might look like. I'm James Eastham. As Julian said, I'm a senior cloud architect at AWS, and the man who needs no introduction is going to join us a little bit later on, Julian. How many of you are actually building with event-driven systems today? I think you're building event-driven systems. Okay, cool, fair few of you. So before we get into any further, I just wanted to start with a little bit of a level set, just to make sure we're all on the same page. And we'll start with the idea of what actually is an event. If we're going to be event-driven and build event-driven systems, we should really understand what this fundamental building block is first. And in my mind, an event is an irrefutable fact. It's something that's happened somewhere in a system. It's something that cannot be changed. I want you all to imagine something for me just for a second. Imagine you're all stood in a room. You're in some like Squid Game-esque escape room type thing. And you're stood at one side of the room and you need to get to the other side of the room. Sounds simple, apart from the fact someone's scattered Lego blocks and upside down plugs all over the room, and the room is pitch black. It's completely dark. And if you've ever stood on a Lego block, you'll know exactly what that feels like. So you could try and get across the room in the dark, right? Or you could try and solve the game, look around for a light switch. And if you can hit the light switch, that's going to raise a light switched on event. That means you can see what's going on in the room, you can get across the room successfully. But it's impossible to unswitch on a light. That's happened, it's irrefutable. If you really want to play the game and try and do this in the dark, of course, you could hit the light switch again, and that will raise a light switched off event. The light switched on, the light switched off. It is irrefutable. You cannot change them things. So if that's an event, what does it mean to be event-driven? If we're going to drive systems by event, let our language drive the business, what does that actually mean? And one of the best descriptions I've heard of this is actually from one of Martin Fowler's talks on the topic, and this is a really excellent talk on event-driven systems if you want to go and check this out. And at the core, an event-driven system is about reversing dependencies. It's about reversing lines of communication. So if you consider the typical synchronous system, you've got service A needs to communicate with service B. And when you look at it from this perspective, it looks incredibly simple, doesn't it? One box, one line, one other box. And it is incredibly simple when things are on the happy path. How many of you ever built a system that has never once strayed from the happy path? I'm still yet to ask that question and get a hand. It's amazing. Because it's hard, right? Although this looks simple, when you actually consider what you need to understand here, it's really quite difficult. Because the first thing you need to understand as a developer of Service A is actually where is Service B? And we solved that quite a few years ago now with something called DNS. But DNS is great, providing that there is something actually behind that address. But what if Service B is having a problem? What if Service B is having an outage? Then what do you do? And actually, I think even more subtly, what if Service B is there, but it's responding incredibly slowly? A 200 response that takes 10 seconds to come back is harder to work with than a 404 that takes milliseconds, if you ask me. So these are all the things that you need to think about with what actually looks simple actually becomes quite difficult. Whereas when you move this to an event-driven system, you flip that line of communication, that line of dependency. So now as a developer of Service A, you don't need to work with all these constraints that Service B puts upon you. Instead, whenever something changes in your system, you simply publish an event. And as a developer of Service B, you're just interested in these events and working with these events. And EDA is fundamentally a communication pattern. It's a way of modeling integrations in your systems. And events aren't a new thing in software. We've been building with events for many, many years. I actually started out my career working with .NET, and I used to build .NET Windows Forms applications. If you've ever used Windows in the early 2000s, I apologize for all .NET developers. It wasn't our best time. But Windows Forms worked completely with events. You had button clicked, mouse hovered, window resized, and then you ran some business functionality off the back of that. And this was back in 2002 when Windows Forms was first released. But if you go even further back, all the way back to 1972, this is an example of some Smalltalk application code. Has anyone ever written Smalltalk? Just out of interest? Okay, some hands. I'm going to embarrass myself now by trying to explain what this code does. The very last piece of this code here, if you look, is talking about events. It's talking about the yellow button getting pressed. So even back in 1972, events were being used to trigger functionality in systems. But actually, these are examples of what I would call technical events. Whilst it's true that events are driving your functionality, these events aren't actually related at all to your business. Button clicked, mouse hovered, they're not helping you tell the story of your business. And even in more modern ways of building systems, like S3 object created events, whilst useful, they're just technical events. Now, invoice uploaded, now we're getting closer to an event-driven system. And that's because event-driven systems trigger business functionality using business events. And that last piece is incredibly important. It's business events that are driving functionality. Things like order created, order confirmed, staff member clocked in. You could look at two businesses in the exact same domain, and they would quite possibly have completely different sets of events driving their functionality. Whereas the technical events are probably going to be pretty comparable. And back when we were all building monoliths, this was less of a problem. Because what was a communication between two parts of your monolith was actually just a method call inside a single running process. So it was kind of less of a problem then. And then in the early 2000s, the idea of service-oriented architectures came along. And then later that decade, microservices popped out of the buzzword bingo box. And we all started building these more loosely coupled systems. And as you increase the number of services you have and you increase the levels of decomposition, you also increase the lines of integration. And back in the early 2000s, the primary method of doing these kind of integrations was with messages and with files. I've built systems that I'm sure many of you have where you put a file somewhere in a location, and then another system comes along and picks up that file at a later date. And if you've ever done that with CSV files, you'll know that that is really, really painful. And this led to the development of the enterprise service bus back in the early 2000s. And these were a popular way of developing integration points between systems. Instead of each individual team needing to own and operate and manage their own integration infrastructure, instead this was shifted out into a central team, into a shared integration resource. And although this uses the term bus, this was for both synchronous and asynchronous integrations. And this central team would then manage this single enterprise service bus, and they will be in charge of operating and keeping that online. And the observant or possibly scarred amongst you will probably notice the problem here, and that problem is that if the enterprise service bus goes away, then you're in a really sticky situation, because now none of your services can integrate with each other. But there's another potential and probably more subtle challenge here. Because around the same time enterprise service buses were becoming popular, one of my favorite software books of all time was released, and that is Enterprise Integration Patterns. And much like Jeremy, I'm also a nerd about patterns. Because patterns, to steal Luke's phrase, allows us to stand on the shoulders of giants. These things that have already been solved, we can reuse in our architectures. And Gregor and Bobby in this book published 65 different patterns of integration, ranging from simple building blocks, like point-to-point message channels, a point-to-point channel being more akin to REST-style communication, where you've got a single producing system and a single consuming system, and instead of that being synchronous, there is some kind of message channel in the middle. This is typically something durable, like a queue. And it makes it really easy to scale your subscribing systems because you can add more of them, and they will take turns pulling messages from the queue. And at the other end of the spectrum, you've got publish-subscribe message channels. And these are almost a complete flip of point-to-point channels. Now you've got one system producing messages onto some kind of central channel, and you've got many different subscribers all subscribing to these same events. And then as you build this up more and more, things start to get a lot more complex. If we go back to them same 4 services from earlier, you've got service A producing a message onto a publish-subscribe message channel. And then there's 3 downstream services that are all interested in these messages. The first one, service C, is nice and simple. Service C just needs to take these messages and work through them in a durable way. So here you're combining a publish-subscribe message channel with a point-to-point message channel. Nice and simple. But then service D has some completely different business requirements, a completely different set of language. And they need to resequence these events into some kind of order and then aggregate them together to draw some insight, some analytics, whatever that might be. And then service B has a completely different set of requirements. Again, service B needs to translate that message into something relevant to its domain and then split it down into lots of smaller messages. Imagine you've got an order confirmed event with an array of items and you want to break that down into all the separate items. So what I'm trying to point out here is that each of these individual services have their own individual language, their own individual requirements that then lead to a completely different set and combination of integration patterns. And this causes a problem back when we were building enterprise service buses, because now, as well as this bus being a single point of failure, it also needs to be able to support all of these different patterns, all the different combinations of these patterns. And if the technology choice that was made by the enterprise integration team didn't fit one of these patterns, well, tough, you need to go off and do your own thing. And it also relied on this enterprise integration team to be able to operate this, to be able to push out changes without affecting other integrations that are already up and running and working. And some of the challenges I've just described there probably remind you of building a monolith as an application developer. These are the same challenges that led us to start thinking about decomposition, to start thinking about service-oriented architectures and microservices. And when building microservices, these points of integration increase exponentially, and that makes these patterns of integration even more important. So you might end up with this really perfectly, loosely coupled, wonderful microservices architecture, all integrated together with a shared enterprise service bus that's then got a single point of failure that needs to be managed separately. And that might lead you to think, why can't we just apply that same level of decomposition that we did to our applications to our integration infrastructure as well? And actually, that's been really easy. Back in 2006, when SQS was first released, one of the original AWS services, that now gave all of you as developers the ability to provision your own integration infrastructure. If you needed to integrate 2 services together with a point-to-point message channel, you had that with a simple API call to provision a queue. And that queue was completely operated and managed and made available by AWS, and you could focus on implementing your business functionality. And of course, since 2006, things have exploded pretty dramatically. The 3,000 Lego block analogy feels about right. But what that actually gives you now as application developers is that you can take these individual patterns that all of you need, these individual business requirements, and apply services on top of that that fit the exact requirements that you need for your specific system. Now, some of you might hear that and think, James, surely that takes us back to the early 2000s, back before the enterprise service bus, back when every single individual team was managing and creating its own integration infrastructure. And whilst that's true, there's a couple of subtle differences now. The first being is that each of these teams don't need to operate that infrastructure themselves. With the power of serverless, it's the cloud provider's responsibility to operate and manage the infrastructure. You don't need to worry about that. And then when you couple that with things like serverless LAN patterns, CDK constructs, that enterprise integration team that used to manage and operate a bus could now spend more valuable time codifying some of these integration patterns and building shared constructs that other people can use. And this is where I'm going to leave you in Julian's capable hands to talk to you a little bit more about how serverless fits into all of this and what the future of development might look like.
Thank you, James. And so James has spoken about sort of integration patterns, and I'm going to dive a little bit deeper into some of the implications. And the first thing we sort of think about is connecting two systems, which we often call coupling. And connections and coupling as an architectural practice is a super important thing to understand when we are thinking about our architectures. But why are we actually connecting systems together? And James and other speakers today have spoken about them. Is it sort of passing files around, writing to and reading from databases? Maybe we are sort of orchestrating some workflows, connecting things together. What about the actual messages? Are they discrete? Are they individual messages? Or are they sort of batches of messages or a stream of related messages that we need to speak to? But there's a lot more also to think about when connecting systems, and you sort of really need to try and understand what you're trying to send or receive, but not just what, but how. Are we talking about sync or async or pub/sub or point-to-point, as James said? Are we pushing or polling? What's actually getting the data from where? Which direction? What format is the data in? Is it spread in different places? Is it individual systems, or maybe individual instances, or some sort of third-party API or some SaaS platform? And of course, what about the failure modes? What about error handling, partial failures, retries, back-off jitter, all the kind of things? Connecting systems and couplings is really important, and it's good to understand that it isn't just a one-dimensional choice, connect service A to connect service B, and we need to obviously think about coupling and connectivity between many of these different facets. And as James mentioned, enterprise integration patterns is 20 years old. And Gregor Hopper, he works now at AWS, but he's had a huge career in building up these kind of patterns, which are so useful. And remember, integration patterns is 20 years old. That's twice as old as Lambda, and actually twice as old as Kubernetes. Imagine that. And there are 65 patterns, codified in the book, and that's sort of 65 different ways to think about how different systems connect. And, never mind, as James says, combining these different kind of patterns. And it's, of course, it's just getting service A to talk to service B, right? But your mental image in my head sometimes is sort of navigating all this messaging kind of thing could look a little bit like this. And it's messages going sort of all over the place, sort of flowing at different kind of levels, different parts of your application. And obviously long and painful backtracking if you misread the sign or you take the wrong direction or miss something that's going to head you in the wrong place. And even at AWS, our services have a lot of functionality and so many features that, this can also be a challenge to navigate. And just talking about SQS, SNS, and EventBridge, 3 services, it's just to get messages from A to B. And there's sort of a Venn diagram over here, which talks about the similarities and also the differences. And, this isn't a pop at AWS services. Everyone takes advantage of this, but this is just highlighting that there actually are so many integration patterns. And this is for very good reasons, because businesses and applications have different needs. They have different requirements that they need to satisfy. And being able to understand these requirements with patterns is extremely powerful and certainly useful. And so if we think about connecting services together, there's often a lot of talk about the boxes and the lines. Service A talks to service B, and the focus is often on the actual service, the microservice maybe that's going to communicate, and that's often represented as the boxes. But I don't think we actually pay enough attention to the lines. Deciding on the lines actually defines a whole bunch of the architecture of the application. And a lot of the messaging services we've been talking about today, SQS, SNS, EventBridge, even other things like Kafka or RabbitMQ or API Gateway, AppSync, Kinesis, anything, they're all sort of partly lines. Even the enterprise service bus sort of is a line, not a box. And if we had to categorize distributed system fundamentals into some sort of different things, we would have coupling, the connectivity, how services are joined together and where the data resides, and then control flow and flow control. And notice there's a difference in how that's mentioned. In which direction messages are actually flowing, that's the control flow, and then how big is the flow, how big is the flow, which is controlling the actual flow. And of course, there's some other things like ordering semantics and delivery considerations, and of course, error handling and retries and idempotency and all these kind of things. But the important thing I want to talk today is about the control flow and the flow control. And there is a difference in what data gets moved between different services and then how that data is actually moved. And part of that is the data flow versus the control flow. And you may be wondering what that is. Well, data flow is the actual cars on the road, moving people around. And control flow is maybe the traffic cop that is going to be directing where traffic is going to be. Maybe it's going to be a sign or a map that you're going to do is show the direction of how the cars are going to get around. And what we see here is service A, community service B, and that's just the top talking about the data flow. But the control flow has different architecture patterns depending on how the lines work. And if we look for a simple messaging control app, that's actually going to be simple. Service A is going to send something to service B, and the message or record or whatever is just going to be passed. But with RPC, for example, A calls B and then gets information back from B. And the return information may actually be the important part of the stuff that's actually needed. So a different pattern. And then with polling, well, A doesn't actually send messages to B. It's B is going to pull messages from A, and B is then going to initiate that conversation to get the data from A. So this is just two services communicating, but very different lines and very different directions, and it's all about the lines, not about the boxes. And the 65 integration patterns are actually functions more often of the boxes more than the lines. And all these patterns are to do with data, not necessarily how data travels between different services. And so Gregor has also updated the patterns to include the control flow, and this is interesting. And you can sort of see these represented in what he calls these little noses and the notches. And I like how Gregor talks about that. And you can see the nose is a little bit that sticks out like a nose, and the notch is a little bit of thing that goes in. And this indicates the direction of travel, how the services connected together, the noses and the notches. Maybe that's going to be the one thing you're going to remember from today is the noses and the notches. And then this means that you've got like a puller, and a puller is going to pull data from some other kind of system, and then something is going to be pulled from it. And then a driver is going to be pulled and then pushed somewhere else. And then a push is pushed to and then pushes somewhere else. And then you've got a queue, which is a bit more of a passive thing, and something's sort of pushed into the queue, and then something else has to pull from this queue. And so you can sort of see the direction for event sources and targets, and polling sources and pulling targets. And actually understanding these little notches, which are often buried in other services, is quite important. You learn about the noses and the notches, and understanding this can help you understand event-driven architectures a lot better. And it's super important when you are building your EDAs. And an AWS example over here, you want to send messages from DynamoDB to step functions, and that is the data flow. But in order to do that, the line actually needs to expand into some other kind of service. So if you're using maybe, say, event bridge pipes, that's going to be a great service. And what's that actually going to do is it's going to pull data from DynamoDB streams, because you can't actually push data from DynamoDB directly to step functions. So the pipe is then going to do whatever it needs to do. Pipe has a lot of functionality. It's going to do some kind of things, and then it's going to ultimately send it on to step functions. And so that line is a critical way to think about how DynamoDB and step functions integrate. And then even within services, the sort of enterprise integration patterns are actually subcomponents within services, and you may not realize this. And you can look at the little noses and nooks to understand the traffic flow. And in this example, we're sending messages from SNS to SQS via an event bus, and it's all sort of a push-based mechanism. Everything is sort of pushed along the flow. They may be filtered, and we may have some format translation within the event bus using input transformers, and this is all different patterns that are living within a service. But what when we maybe change the target? Well, things actually change. So if we decide, well, hang on, we rather want to send from the event bus to API destinations and no longer to SQS. Now this means, well, this is an external service. We now need to configure maybe the invocation rates. And this is then flow control, controlling how many messages are sent. And then to manage this internally, EventBridge needs to have some sort of queue to store that message temporarily until that can actually be processed. And so a pattern which is called a driver needs to pull messages from the queue, and then when it has available capacity for the target service, it needs to be able to send to that target. And the queue obviously also can't just build up forever, so it needs to have a time to live value that can expire messages from the queue at some time. And again, this is another version of flow control. You need to control the flow through your application, the size. And if we want to simply reverse the traffic flow and maybe, application requirements change and we maybe want to change everything. So instead of going from SNS to SQS, we now want to go from SQS to SNS. Simple application change, correct. But now we need to use a different service because we need to use event bridge pipes, and because we need something to pull from SQS because the noses and the notches are different. And SQS is a polling source, and we need that driver because we need to also control the batch size and we need to control the batch windows. So there's something there that we need to handle things temporarily. And the pipe is also going to maybe do some filtering, or it's maybe going to enrich the data from a third-party API or something, and then ultimately it's going to push it to SNS. And again, now, if we actually change the destination again to an API destination, some third-party service on the internet, for example, we don't actually have to change the model. We already have a driver, and the invocation rate can then define the batch size and the actual window. So there's sort of a match-up between them. Again, configuring the flow control. And understanding the control flow and where the flow control is managed really helps understand the different messaging systems fit together. So how do we actually configure all of this? Because surely that's going to be hard. And as others have said today, we preferably really want to code these things, code these lines and these boxes to be understandable and repeatable. But classic infrastructure as code tools sort of actually come from a nested world where we sort of had an EC2 instance and maybe something like a database instance, which would be inside of VPC, maybe inside a region. And this is a sort of resource hierarchy graph where we're mainly thinking about the different boxes. But actually, if we're talking about modern applications, and cloud automation is way more fluid than this. It really is actually exposing those lines a little bit more. And when we want to talk more about application topology, how we're going to put things together. And there isn't as much infrastructure as with the resources, but we move to this world of application topology and how the services communicate. Infrastructure definition and application definitions sort of merge, and that's interesting. And I think actually a slight sidebar, I think sometimes this is one of the things that people don't understand about serverless. Because often we talk about serverless and we say, yes, it's all about removing infrastructure like load balancers and instance types and network constructs, and you never need to look after that anymore. And that is true, but it also means you can actually now model your applications using new things like functions and data stores and workflows and events. A whole different way of thinking about things where it's application constructs rather than just removing infrastructure. And then you can also imagine how you need to then build these applications. Requires us to then decide on the functionality, use the patterns from Gregor's books and other ones we define within our business. And then we need to translate that into a runtime model and basically decide which service are we going to use. Is this going to be SNS? Is it going to be SQS? Is it going to be some other third-party service? And only then can we then program how to actually use that service. And this could be directly configuring the API, or maybe you are going to use an infrastructure as code tool, and it could be CloudFormation, CDK, SAM, Terraform, pick the one you enjoy. And this means we sort of have to choose how we're going to run it before being able to program it. When actually, what we'd like to do is sort of have our functionality first, and then we actually want to program against the pattern, and then something figures out how best to run that. That would be great, right? It sort of seems a bit the wrong way around. And so we can sort of think of this idea, which Gregor and other people are thinking about. How can we model functionality without having to get into the weeds of the actual implementation? How can we create useful abstractions for what we want? Now, this doesn't really exist at the moment, so like Jeremy's talk in the beginning, we are sort of talking about some future ideas of how things could possibly happen to make our cloud architecture better. And here on the left-hand side, we can sort of see a pull pipeline, and we want to get messages from the table stream ultimately to the event logger stream, and we need to maybe filter and dedupe and transform it, and then it's going to send it on. And simply by changing one of the attributes, the .from to the .endpoint, we could change this from a pull mechanism to a push mechanism, and that may satisfy your new application architecture. And then also if we need to consider the flow control, and then maybe we do need to introduce a buffer, i.e. a queue, and we just add that into our little bit of code or pseudocode, and the abstraction can amend the resources as required. Now, as I said, this doesn't exist, but it's an important and interesting way to think about how we can maybe think about those noses and those notches and how that's going to impact our architecture. And hopefully in the future, we're going to move to a world where this can all be nicely codified. But what does exist today is a number of companies which are already doing interesting things into what's being called infrastructure from code or application architecture as code. Now, I'm not sort of personally endorsing all of these. I'm not saying run out and go and buy them, but it's an interesting way to think about how people are taking the cloud into the future, and particularly serverless into the future. And one of these is Winglan, and it's actually built by Ella Ben Israel, who originally created the CDK. And he said the CDK is great, but there's more that we can do. And so Wing Lang's idea is that application code and infrastructure code really should coexist. And here you can see you start your application, and I love the beginning, bring cloud. I think that's the most succinct way you could probably ever use a cloud service. Absolutely love that. And then you've got a new bucket, and you're going to then define a bucket, and you're going to write then some custom function code that's going to simply just put data to that bucket. And well, what Wing's going to do is it's going to then compile that code into an application artifact. So it's going to be a Lambda function in a zip archive, imagine, and also as well as creating the S3 bucket, and then also just figuring out and building the IAM permissions to do exactly that. You can figure it out from your code. And what's also cool is on the right-hand side, you can see there's actually a local developer sandbox, which Wing Lang has built. And so you can actually test this, you can upload this, you can do everything locally without having to do things in the cloud, sort of fast in a loop. And then a whole bunch of stuff happens. And then you can then also deploy this, and it does sort of compile it into Terraform or CDK or things like that. So also if you need to break out of the Wing Lang programming model, you can understand exactly what's being done. And you can also do different things. You can create services that run in containers, or you can create functions that run, obviously, in functions. You know, bringing your application and application code and infrastructure code together in one place. And you may have heard a little bit this morning from Jeremy about AMP, who is doing something quite similar, and that's also exciting. And write your application code, and AMP is going to work out just how best to run your applications. And this is actually abstracted from creating your resources. You create your application code, you're going to add a task, you're going to add a schedule in your app code, and then the magic just makes that all happen. And it is sort of magic, and it's cool magic. An AMP service is also more than just compiling code. AMP can actually decide, and Jeremy sort of hinted at this, that it should decide just where your services run and whether should they run in a container or in a function based on the runtime introspector. And they can figure this out because they can, it's going to depend on the time it needs to run, maybe the resources, maybe the concurrency, and AMP is just going to manage it all for you. And you may not even know whether it's running in a container or running in a function because AMP can just handle that behind the scenes. The tagline is, just write application code. And of course, AWS in the cloud also doesn't just stand still. Previously, one of those features like in-order events had a very different architectural pattern and offer much lower throughput. Well, both SQS and SNS have dramatically increased their FIFO throughput, as you can see here. So you can use ordering in your applications when previously maybe you were blocked from doing that. Look at the example over there, SQS, 18,000 transactions per second. I mean, that's an absolutely huge amount, and it's just pay as you go. So the point is that cloud is continually evolving, and you can always take advantage of new functionality. Another one was EventBridge, drastically reducing their latency by 80%. And we actually had support requests coming in going, hang on, I think my application is broken because my events are being delivered much faster than before. What have I done? Please tell me what's broken. And the cool thing is there's some happy customers sort of finding out that actually it's just the cloud improving before them. But this EventBridge change also now opens up some other possibilities and highlights another pattern and way that you can do things. And we always talk about synchronous and asynchronous and how you want to do more things asynchronously because it allows your applications to react, to be event-driven, and do more. But the sort of the problem is, which everybody knows, is sync is often seen as a sort of very fast response, and async is seen as, yeah, that's the back-end stuff, and that's a bit slower, but often it doesn't matter, but maybe it should. Well, this is now a different thing that you can now do in the modern cloud. And let's see how this could work maybe in a modern app. And a common architectural pattern, if we think about it, is often going to tightly couple the needs of your front-end application, and maybe this is going to be a web or mobile site, or maybe even something from a desktop. And it's going to then connect that with an optimized back-end API. And this has actually got a term, it's called front-end for back-end, and it's a great way to decouple parts of your application. And the goal of the layer is to be able to have this sort of middleware in the middle that is going to handle some orchestration and aggregating data, and then supporting also different kinds of clients. And then you have a front end that obviously needs to get updates from a back end. And in fact, many apps have front ends that need to get updates from multiple back ends. That's going to be a common pattern. And maybe this is even going to be using micro front ends on the front end side of the client. And sometimes you may be even going to have different clients who you don't want to run maybe the same API for all your desktop clients and your web clients because that could get unwieldy, and maybe you want to have different APIs. So different backends for front ends can allow that to happen. And of course, those backends are doing things. They're passing messages around, they're communicating with each other and with other third-party services, doing a whole bunch of stuff. And so using EventBridge to route messages is really useful. And so you would love to use EventBridge as your backend because you're probably using it already, and your services are communicating, but you also want the front end to be able to get updates. And so now we've got new integrations with things like between AppSync and EventBridge. And so this means you can actually asynchronously route events to AppSync, and your GraphQL subscribers can just get immediate updates. And that is cool because GraphQL is a super powerful mechanism for aggregating data from multiple different sources, and clients can just get the data they need without having to do multiple round-trip requests to different backends or different APIs. And so actually reducing this EventBridge latency makes this even better. 80% less latency now makes this possible. So we were talking about those sort of spinning wheels earlier this morning, getting rid of them. Well, this is maybe a way to think about that. Opening up a whole set of different use cases, and it means the front end is really nearly as responsive as a synchronous call. And back to code, or rather less code, because we all like that, is that you can model this quite easily in infrastructure as code and even in the EventBridge console. You just select AppSync as a target, and then you can actually view the GraphQL mutations. You can use the input transformers, again, another pattern, to configure the formats, and your backend events go to your GraphQL subscriptions. So think about this. What if sync and async were not far off from a latency perspective? What patterns could you use this for, and how powerful would that be? And other companies are also reinventing the way that modern messaging works. Kafka, for example, was started by LinkedIn in 2010, and that's a super popular event streaming platform. And Kafka was very much a way of building a streaming data platform for super high scale and throughput, trying to do that enterprise service bus, trying to build that ESB in a whole new modern way, but it was sort of built before the days of the cloud. And traditionally, Kafka is very infrastructure heavy, and and it needs to be because it needs to support those applications and that throughput at high scale. But what is cool, this is the modern cloud, and many companies are now building serverless versions of Kafka, including AWS. And so companies are reinventing Kafka for the cloud and for the serverless world. And Red Panda is one that we know about. And this is sort of shipping the Kafka application just as a single binary to avoid a lot of the distributed systems hassles of running Kafka and things like Zookeeper, which is a part of Kafka yourself. And it just makes it much simpler and much faster. It's Kafka API compatible, but a complete reinvention of the compute part. And then you've got WarpStream, which is taking other approaches. And this is modernizing Kafka with some other interesting things it's doing. So WarpStream correctly says that, well, having Kafka clusters that actually span availability zones, means you're paying for a whole bunch of inter-AZ charges. That's just the way it works. And all those messages need to be replicated for resilience, but it means you are paying for that inter-AZ bandwidth if you're running your Kafka on EC2. Well, even if it's managed by somebody else. But other AWS services have inter-AZ replication as part of the service, just part of it, like something like S3. So instead of replicating your data sort of traditionally between your EC2 instances, why not use S3 actually as the replicator under the scene? And this means you can dramatically reduce the infrastructure you need and build on the great AWS cloud primitives. And Confluent, who is huge in the managed Kafka space, also recently announced freight clusters who do a similar thing. The brokers are also stateless, and they also batch up data and write it to S3. And they say it's up to 90% cheaper. Of course, it's not going to be as fast as if you could just write straight to SSD. Can't believe I'm talking about SSDs at a serverless days, but we are talking about speeds and feeds today. But for many workloads or analytics, or where availability or cost is more important than performance, this can be super helpful. So a quick tour to show that something even big, and some people can rightly say Kafka is quite a clunky thing, built before the era of the cloud, is being reinvented for the cloud and the serverless era. And the event-driven world is super old. James was talking about in the 70s on the on-click events. As soon as we've been building software for many, many decades, we have been reacting to events. But it was always hard, and it was always complex. The enterprise service bus started to get things moving in the right direction, and the patterns and the integrations were all sort of great. But now with the cloud and the serverless, using those patterns and implementations are seeing a whole new lease on life. Serverless is so much easier to use to be able to bring all those patterns and to connect the different services. And I think it's only going to get better. The cloud and the serverless is an amazing enabler for doing a whole bunch of things. People are thinking that all this messaging and serverless is an old fad and it's marketing, and to wind a horrible joke is sort of going down with the Titanic, but it certainly isn't. Cloud and serverless. I love serverless. It's in my heart, and I can even be worse and say maybe my heart will go on. Thank you. Wow. If that's the end of your day and I'm standing between your carbo loading from the day and your beers, I've done my job. So the point is, EDA's day has come, and I think it's going to be great, and it's a great future. And also want to say thank you so much for coming here today. We've heard amazing things from all the different talkers. What a privilege it is to finish off the day with James and hear so many things and talk to different people about kind of things. Also just want to mention the awesome AWS team at the back. Don't forget, you actually have an AWS team here in Northern Ireland. If you've got some support calls going to, you're worried about all it has to go to America or further south down in the island, you've got a local, really responsive, awesome AWS team who are here to help you. So, at the back here, please say hi, and anything you need, they'd love to help you with. Thanks so much for joining us here at Serverless Days. Thanks to all the other sponsors. Thanks to the organizers. Thank you very much.